All right, guys, this video is going to be a little nerdy, but it's going to be really exciting. And really lucky to have Chad back again for this segment because this is where his expertise in. As most of you guys on the pay channel know, we have been doing diagnostics on automotive network systems, and particularly the CAN system. And what happened actually is Chad is a viewer on both this channel and the paid channel, and he was watching the networking on the CAN diagnostics and how to read CAN signals using the scope, and also on a DVOM looking at termination resistors. All that is on the paid channel. And he was watching that and he says, dude, you can do so much more than that because you can actually decode those signals. So for example, in that video, I had mentioned how when I get these signals off the network, and we are going to demonstrate that here through a couple of methods, one of the things is I showed that you get thousands of messages per second, and you get all these messages and you can see them, but you can't tell what's what. You can't tell, well, this is messages from the brake module, and these are messages from the nav system, and these are messages from the powertrain. You just get all these signals, and you can't really differentiate them, but you can tell if it's a good signal, and if there's no signal, or if it's shorted to ground or things, all that stuff we cover. Well, Chad says, actually, that's not true. You can actually take that information and decode it and actually isolate those systems, and not only isolate them, but get right down to the bits and bytes and see where there could be errors that could explain some certain phenomenon. And not only that, but he says he has a way of doing this with what, like a $15 logic decoder?
Yeah. It's called a logic analyzer, and they sell
logic analyzer.
Yeah, for very cheap. They're not able to do as much as an oscilloscope, but they are able to read the data streams.
And it will read the data streams to the point where you get to that decoding. So you won't see the waveforms that I'm going to see on my oscilloscope, but it doesn't matter because whether you do it with a picoscope or whether through his method, you get to decode those waveforms and isolate different modules. And what we're going to do is I'm going to do that because most of you guys are familiar with the oscilloscope, and my picoscope, Chad showed me, has the ability to do this decoding. So I'm going to set up the picoscope. We're going to do what I usually do, looking at the waveforms, and then you're going to walk us through taking it further than that to actually decode those signals. And then Chad's going to show the way that he does it for like $15. So, yeah, why don't we set up? So what you need me to do is to set up like I usually would if I'm going to read CAN signals on a network through my Pico, right?
That's correct.
All right, well, I'm going to go ahead and set that up. So guys, I've mentioned this before when we were covering CAN diagnostics and network diagnostics, how nice it would be to have a breakout box. And I said that now that I know how to do this stuff, this is going to be my next purchase. And indeed it was. So I did purchase this breakout box. I want to say it probably cost somewhere around $30 or so. This is going to be really nice. Not only makes it a lot easier for me to make my connections because my ALDL port is broken out for me, but also we're going to piggyback Chad's equipment onto this as well, something that would be really difficult to do if we didn't have a breakout box. So this makes things a lot easier. The other thing you'll notice, I got this one because it has another port where I can also connect my scan tool to it, so I can use my scope and my scan tool at the same time. And based on what Chad's saying, this will be even more useful because now I can use my scan tool to make bidirectional commands and probably change some coding that we would be able to see as a result, so I can look if a module isn't responding. So while this is not necessary, going to be highly recommended. So I'm going to go ahead and connect this in. We're going to set channel 1 on the CAN high. Going to set channel 2 on the CAN low. Obviously, we need a ground. I'm going to just piggyback both my channels onto one ground. You can actually use either a chassis or signal ground. I think I'm just going to go ahead and use the signal ground, assuming there will be less noise than everything else being on the chassis. Like that. Now I can connect my channels up to my picoscope. With this being a kind of an advanced CAN, my guess is just having the door open, it's going to send messages, but I'm not sure. What I'm going to do is I'm just going to turn key on, engine off, and that should send plenty of signals for us. All right, so we can see I've got some messages here, but I am far from optimized right now. So one of the things, my voltage setting for CAN signal, we know we want to be considerably different here. So probably around 5 volts is going to be optimal. Means I got to bring my channel B down 5 volts for my opposing signal. We are running very fast right now, so we need to separate out our signals. Now we're getting somewhere, and it looks like trigger is going to really help here. So I'm going to add a trigger. Like that. Okay, Chad, so I've got a signal up here, and guys, as you can see, we've got just tons and tons of data. We can clearly see, based on the amplitude of the signal and the frequency of the signal, that we have a good CAN signal here. There is no question about it. What I was, of course, saying is there is no way I'm going to look at this and go, oh no, there's no brake module communication, or there's no, there's a corrupted communication from a PCM module. Obviously can't do that. And what Chad's going to do is walk us through how there is a way, actually a couple of ways, that we can actually decode this to break it down into individual messages, and I am really dying to see that. So Chad, help me out here. What am I going to do in order to decode this signal?
Yeah, so we should have something in your software there to be able to add a decoder.
Yeah, so I did a little homework before you drove up here, Chad, and I did find that there is a serial decoding button here. I believe I need to freeze the signal first, is that right? Or can I run that? I wonder if I can run this while I'm running it. Oh, we got all kinds of choices of decoding. Mm-hmm. We've got several CAN ones, so how do I know which one to use here?
Yeah, your car networks, and you went over this on your paid channel quite a bit, so we'll just go high level, but yeah. Your car has several networks and several different types of ways to communicate. So typically we're just going to use the first one, which is CAN, but if this were a LIN signal, we would use LIN, and if you start to see, we'll go over this later, but if you start to see some errors, there's a possibility it could be CAN FD, but today it's such a new thing that it's probably going to be a luxury car of the current year or something.
Like a Mercedes may use those. Or, oh, okay. I noticed that there isn't a lot of the older networks that I described, things like J1850, things like that. Is that just not available on here, or can those not be decoded, do you know?
That's a good question. It's my understanding that some of those are not necessarily lower layer networks. And so those might be a higher layer. We'll kind of get into the network layers on the whiteboard after this. So we'll touch on that a little bit more there. I could be wrong, but many of the things like OBD, for example, you don't see here. That's because it's on a higher layer.
Okay. And also one of the things I want to do, a lot of, it doesn't, to me, I'm seeing 2 channels, so I'm fine with this. A lot of people are kind of more used to seeing something more like that in a CAN signal. But again, it doesn't really matter. It's still just 2 signals, but just because I know a lot of people are, kind of a little more to looking at it a little more opposing like that. I'm just going to go ahead and leave it like that. We'll go back to our decoding, and I'm going to go ahead and choose CAN as you suggested. I'm going to hit next, and now it's asking us a bunch of stuff that I quite honestly don't understand.
Yeah, the defaults are pretty good here. In my experience, most CAN networks run at a speed of about 500 kilobits per second, which is the default. They can go up to 1 megabit per second, which is twice as fast. And they can go down as low as, I think, 100 kilobits per second, just depending on your vehicle. You may have to look that information up specific to your vehicle. Okay. But for this one, we know it's going to be 500, so let's leave it
I'll leave that. Now it's asking me whether I want data from channel A or B. It honestly shouldn't matter.
It does not. It's an opposing network, so it's duplicated.
All right, I'm just going to choose A then. And now when I did that, it brought up some other criteria to set.
Yeah, I would leave those the same because the protocol does specify the sort of voltages that you should expect, and you should always be getting those. So if you had to adjust these, it would be because you're actively troubleshooting a problem, because it should fall within that range.
Yeah, I understand what this is now that you said that, because this is my threshold voltage up here on my channel A. So that actually makes total sense to me now. Okay, that totally adds up. Let's go ahead and click next, and now we've got, this gets worse as we go, Chad.
So the data basically can represent anything that they've sort of chosen to. So for example, you might have a light come on your dash, and that may only require 1 or a 0 to say that light's on or that light's off. And so that's why we work in binary data. I would recommend using binary. It's a little bit longer hand, but it's a little bit easier to understand than hex. A lot of software engineers
Chad, but okay.
Most software engineers would probably use hex here, though, just because it's much smaller and easier to work with.
All right, and then it gives the option to finish here. So I'm going to go ahead and finish that, and it brings up it brings up, well, to me, this almost looks like a genetic code for DNA. But, well, you know what, Chad? It's actually the same thing, isn't it? It actually is the same thing, because what this is doing, I bet, is this is breaking down specific messages from our raw data, right?
That's correct.
It's almost like genes, and this is my DNA strand. I always have to translate it to something that I can identify with. But is that about what it's doing? It's basically translating messages here. Let me do this real quick, Chad. I'm going to let you describe this. But what I want to do is I want to zoom in on this, and then maybe that'll help us. See, now we're getting some binary data down here. Chad, do you want to take over and describe what we're looking at here?
Yeah, absolutely. So this entire thing that you see here from here to here is a single CAN frame, and every single network is broken up into frames. A frame is basically the largest single packet that can be sent, and after a frame, when you have to sort of send more data than can fit in a single frame, it's split up across multiple frames. And so as you go through here, you're going to see basically the way a protocol works is you have sort of an agreement up front that we sort of do this a certain way. And that's how you can make components like this picoscope that integrates with this car, and when the two people didn't necessarily do anything directly to ensure that happened. And so why that's important is our picoscope here is able to decode this and turn this into the raw data that's being used. And so as you can see here, we have sort of different fields, and the picoscope software, I believe, will actually tell you what each of these fields are. Let's see. I don't know if that was a good description, sorry.
No, it's okay. Nobody's going to understand it anyway.
I wanted to show first the sample rate is probably too low.
Oh,
and
is it?
so,
okay.
So we're getting some weird, a little bit of weirdness.
Chad, you were saying the sample rate may be too low. This means I may need to do some better scope settings. Is that what you're saying?
Yeah, typically to read the logic, you need at least 4 times the sample rate than the bit rate you're reading.
All right. Well, you know what? I actually do believe I can figure out how to do that. Okay. By the way, I noticed you can't actually decode in real time. It's still decoding, right?
Yeah.
Yeah, that's pretty cool. I don't know that it's useful, but it is kind of neat.
It's probably correct.
It may be, but you know what? I do admit I don't really want that on there. And what we can do is we can increase the sample rate, I believe, if I go to my time base and sampling and I can go to fast, which should probably quadruple my sample rate from 20 megasamples per second, and I think if it's more than 80 megasamples per second, I'm going to say that I'm on a different technology than most automotive. So let's see if that makes it go away. It looks like it does. So I think that may have worked, and let's do that again now. So let's stop my signal, and then let me zoom in on it again. And just to make sure that we're dealing with accurate data here. So I'm going to catch this frame. How's that?
It looks good. I don't see anything wrong with it.
All right, great.
So here we'll go on the dry erase board to sort of break down what each of these fields mean. But this decoder is really nice because what it does is it actually goes in and sort of marks your different fields for what they are. And you can see in the picoscope, you can actually see the waveform alongside of it, which is really nice. On the logic analyzer, you're not able to do that, but we'll explain that later. And so you've got different fields here, and each of these fields have expected data that sort of corresponds to the components of this packet, and then the payload is sort of this purple part. So that's the actual information being carried across, and the rest of this is control to sort of facilitate the negotiation of data. And so you've also got these stuffed bits. You'll notice these occasional bits, and what those are for is so that the CAN bus doesn't stay silent for too long, so that each component can stay in perfect time with one another.
It looks to me like the binary is a little bit opposite what a lot of people would expect, because it looks like the zeros are kind of a high voltage, like an on my square wave, and then the ones would be the off or the lower voltage. Is that what I'm seeing here?
Yeah, that's correct. The CAN network's very interesting in that it has sort of a dominant and recessive state, and those get translated to, I believe its dominant state is the 0 and recessive is 1. The reason why this network is designed this way is because when you're in recessive state, that means that if somebody else sends out a dominant state, it will override that recessive state. So what that means is when we're doing this very first part, it's called arbitration. And the way this works is basically it's sending out a bunch of data, and it's expecting this to be zeros, but it's also listening at the same time it's sending that data out. And if it hears someone else speak at the same time, that means that it lost arbitration, and so it will remain silent for whatever other device is communicating on the network. That's called packet collision. And it works very different here than in Ethernet, because in an automotive network, it's very critical that messages always get across.
Wow. Yeah. I'm hoping somebody understands that, because that is above my thing. I will have to probably watch this video myself several times, Chad, to be honest. But at the same time, though, I do know a couple things, and one of them is this idea of decoding a network. So, Chad, what I'm thinking is this concept is actually what my scan tool does. Is it not? Because what my scan tool does, there's not 90 different things that come into my scan tool through 90 different wires or something. It all comes in basically through the CAN network. So my scan tool is getting all the information from the car, everything live data that I've been looking at for years now. And it never really occurred to me, but when I'm connecting into the ALDL, in some cases, on some protocols, it's one single wire that's giving me all the PIDs for my scan tool, but it is data that looks like this, and the scan tool is parsing it out to the individual modules to get those PIDs. Is that what is actually happening? Because it's just occurring to me now.
Yeah, that's absolutely correct. So basically, if I were an engineer tasked with, I need to build a scan tool, right? First thing I would do is build a tool to sort of decode these frames. And then the second step I would do is write software that would basically take these frames and kind of combine them, and then I would find a way to read the IDs and sort of map that data to what it actually belongs to. And so once I had all those pieces together, I'd have the capability to basically read this data and show it to the user in sort of a meaningful way.
Yeah, exactly. No, it totally makes sense to me. I wanted to bring one other thing up, just something that I heard, and see if you can validate if that's true, and maybe we can actually demonstrate it on here. What I believe, from what I've heard, is that when these messages are interpreted by the car's PCM, and in this network, and not by the PCM necessarily, but by the BCM, all of these modules, that they don't actually use all of this raw data from this frame here as it is. What it actually uses is a subtraction of the A channel that I have minus the B channel, and that result, that difference, is actually what is used to do the interpretation. And it isn't really from this double data signal. It's actually from one signal that is the result of subtracting the two. Is that accurate?
That is my understanding, yes. So when what you kind of have to understand is when they design the waveform that you're looking at here, it's very it has to do with physics. Their design choices are based on the physics, right? So they need to be concerned for electronic interference, all kinds of different possibilities, a loose wire in the middle of driving, things like that. So a lot of this really is a little bit counterintuitive because of that.
Huh. So, I can actually, I want to see if I can simulate that here real quick. What I'm going to do is I'm going to go over to and actually it was already here. I'm going to go to math channels. What I'm going to do is do A minus B, like that. That's going to generate a third channel, I believe. That one right there, the purple guy. And that is actually the data that is used.
Yeah.
And some of you guys are probably wondering, well, wait a minute, how can I get that from here? Because these are opposing. So if you're subtracting B from A, you should get 0. Well, remember our amplitude. Remember, we're up at about 2.9 volts or whatever, almost 3 volts up here. And then down here, you see we're at about 1.5. So when you're subtracting them, you're getting about, a little over 2 volts, and that's why we see the difference here. So it's not like this center line is 0. So just in case you were wondering that, guys, because it looks like you subtract B from A, you get 0. But Chad, this would be the actual data signal that the modules use, right?
Yeah, and it's a very good observation that this is not 0. Could you imagine a reason why you wouldn't want that to be 0?
Well, I guess it's because if you have an off signal, you can't differentiate it from maybe a ground fault or something, possibly. I'm not totally sure.
Absolutely, that's one reason. Okay. Another reason would be, though, what if we are driving along and a wire's been cut? Immediately the equipment knows the wire's been cut.
Yes, it can differentiate the 0 on the square wave from a true 0 voltage.
Yeah, and so that it will enter in fail-safe modes in order to keep you safe as you're going 80 miles an hour.
That's a good point. So the other thing we got to cover here, Chad, is what this data is down here. And then we want to kind of go to your method of doing this, where you claim that people can get at least to this level of data for
$15,
right? $15. Yeah. We got to see that. But what do we got going on down here?
Yeah, so this is the information once it's actually been decoded and input into sort of the next step. And this is why we kind of refer to this as layers. So this is your physical layer. But then you get into the data link layer, and that's when we are decoding this. So what you're looking at is data link layer. So you're already at level 2. And so if you were to ask a network engineer, hey, I need your help with a layer 1 issue, they would be looking at the physical cables. And so now once we're in this layer, the data could, for example, have like a checksum error. So if we highlight over this, we could actually see it says that the CRC is valid, and it calculates the CRC. And what that basically does is say, this data, when we apply a mathematical function to it, we create a sum, and we also transmit the sum that we are intending to send, and it checks that against each other. So if, for instance, this were to disagree with this, we would have a layer 2 issue, and that would be what we're looking at here. And so now...
CRC must be some kind of redundancy code, or what is a CRC?
It's a cyclic redundancy check.
Okay.
And so that's a very common type of basic checksum. And you can look into that more kind of on your own, but it's sort of generic across all computer science. And it's just a way to do sort of a sanity check to make sure, okay, this data really is what we thought it should be.
Excellent. So if this CRC was not checked, that would be an indication that we have some kind of error that is not mathematically making sense.
Yes.
And that would help us to focus in from a diagnostic perspective.
Absolutely.
You must just be fighting chicks off all the time with this. I bet this, really hit at parties.
It's a real problem.
It is, I bet, yeah. So we want to do a couple things. One of the things I did want to do, first of all, I again wanted to thank C5 Diag, the viewer who actually gave me the picoscope. And as you can see, I am definitely making more use of it every time. I really can't thank you enough, man. That was just amazing and continues to help not only me, but obviously a lot of people as well. However, one of the things we also want to do is 2 more things. We want to show your method for doing what we just did at 1/50th of the cost, which will be amazing. But also what we need to do is we need to bring this to a level where we can use it for diagnostic applications, because that is what we do on this channel. So while this is all great to know and it's great to see, and if nothing else, it's a little bit mesmerizing and it's just cool to see this amazing wizardry, we do need to bring it to a level where when we have CAN network problems, when we have BCM problems, when we have powertrain communication issues, when we get on that scan tool and we see a network communication down, how can we use this to be more targeted in our diagnostics? Because right now, the way that I have to do it is I can just determine there either is or is not a network issue, and we're going to find out later, I believe, that you're going to tell me that I'm wrong on that, because I'm going to think I don't have a network issue when I could, and I'm very eager to learn about that. And then what I have to do is I have to systematically probably unplug modules, things like that, and be very systematic at finding out where this issue is that's pulling out my network or corrupting it. And I believe that you have better ways of doing that you're going to be able to show us. But most importantly, you're going to be able to show these guys how they can do it, as I did, for a fraction of the cost, and I am dying to see that. So let's go ahead and get started on that.
Absolutely.